So this is a gentle introduction, very gentle introduction to algebraic geometry, and I thank the director of MSIB, Professor Venkatesh, to have given me this opportunity. So, what is all about algebraic geometry? Uh, this this involves points in the Euclidean space, but we have this notion of the affine space, which comes out as let's say we fixed an algebraically closed field K, and the points we consider come from Kn, that is the n-dimensional space over the field K. So that's the affine space where it's not quite the vector space because we don't have a fixed null vector, the origin. So that's the affine space. So I have this more like a semi-historical introduction. So the Italian school of geometers uh, uh, looked into this a special kind of geometry which involves algebra. As we can go further, we'll check that. So especially the Italians wanted to have a geometry which gives you a perspective, three-dimensional perspective through projective geometry, etc. So that's one of the motivations for algebraic geometry. Also, in classical mechanics, the school led by V.I. Arnold and others understood the spaces via polynomial equations. So the ring of polynomials in with coefficients from k, that is k x1 x2 dot dot xn. That's the important aspect. And as we can see, not only just polynomials but rational functions f by g, where let's say fx comma y is a polynomial, gx comma y is a polynomial. We look at the locus of such a function, and that is the one of the motivation. Even when you're looking at mechanics, when you're looking at curves uh, passing through some vortex point, etc., we want to understand the neighborhood of such points. That's the idea. Also, when you look at classical aspects like Stokes theorem, etc., one is interested in looking at polynomial functions, and that led to some algebraic computations. So, as I mentioned, V.I. Arnold is one of the pioneers. Even before that, Italian geometers, Enrico uh, uh, Castelnuovo, etc. These are some of the names I remember. So, also algebraic geometry has been playing a pivotal role in number theory because if you can see the proof of Fermat's last theorem, you can see that the uh, the fact that there are no solutions for the equation x power n plus y power n equal to z power n in integers is through understanding the possibility of elliptic curves, which leads to uh, the arguments therein. So a lot of topological arguments and geometric arguments play a role there. Even cryptography, we look at, for example, toric varieties, Tori-based crypto systems. So again, algebraic geometry is used. So uh, yeah, so looking at geometry as such, we are looking at okay in the introductory class. Let me look at the k being c, and K is this field Cn. So Cn, for n I take 2, so that we are just looking at polynomials in two variables. So look at some subset S of C2. If this happens to be uh, the zero set of some bunch of polynomials, then we can call it as an algebraic set. More precisely, affine algebraic set. If we instead look at uh, projective coordinates, then we get projective algebraic sets. But right now, I'm just focusing on affine algebraic sets. So one looks at points in C2, or in more generally Cn. One looks at lines in C2. One looks at curves in C2 and tries to see if they can be understood as via a bunch of polynomials. In a very simplistic way, let me introduce. If you just have one function, let's say fxy equal to 0, f being a polynomial in cxy, then if you look at all the solutions of this, because C is an algebraically closed field, we do get solutions, and set of all solutions forms an algebraic set. And that's a very simple example. Even if C is not algebraically closed, we can still talk of such geometric objects. For example, if I uh, take it as a real plane and look at set of all xy satisfying x square plus y square is equal to, let's say, 1, we get the unit circle. So unit circle is an algebraic set, and algebraic sets which are irreducible are called algebraic varieties. That's the fundamental objects in algebraic geometry. So that's the point here. You could get the affine algebraic set as union of two connected sets. So connected in some topology. Basically, one looks at Zariski topology. So let's not be too uh, uh, what do you call uh, too much uh, focusing on the topology aspects right now, because the topology seems to be a little vague here. But let's say you have two x is union of two sets x1 x2, and this is that is x is reducible into exponent x. However, if you have an algebraic set which cannot be expressed as a union of two such sets, which is itself a single component, it has a single component, then it's called as irreducible set. So an irreducible algebraic set is called as an affine variety. Similarly, if we look at projective space Pn, and then we look at uh, such algebraic sets which are irreducible, then they are called projective algebraic varieties. Now I want to focus on a little algebra that is required. I'm assuming that my undergraduate students do not have much basics. So let me recap. You have number systems like the natural numbers, integers, complex plane, the complex number system, the real numbers, rational numbers, etc. You see that they are groups. They have algebraic structures. Some of them need not be. For example, the natural number system is not a group with any algebra binary operation, but the rest, if you could see the real line, can be endowed with a group structure. Simply take plus as a binary operation. Q plus is a group structure. Z plus is a group structure. So you have group structures, but in schools we also see them to satisfy the closure law, the associative law, the inverse element property, the identity element property. That forms the axioms for groups, right? So you see all of these examples of commutative groups. Look, these commutative groups have an additional property here. I mean, these the ones that I'm looking at, not n by the way, but all of them when we study at the school level, we also simultaneously define multiplication. So uh, multiplication in all of these systems is closed and associative. So if you look at the ones which have got the additive group structures also have the multiplicative structure which satisfies closure law and associative law. So such number systems or algebraic systems in general are called rings. Okay, and since these involve symmetries, naturally geometry comes quite naturally, and that's what I want to say that uh, clo- the ring structures, that is, let's say R is an empty set with R plus is a group, abelian group, and R with multiplication is a satisfying closure law and associative law, and also these two are combined with the distributive law, like for x a comma b in R, x times a plus b is x times a plus x times b. This is the distributive law. If all these are satisfied, then it's called as a ring structure. So for Z, let's see, Z is a ring with 1. That is, it has a multiplicative identity, sometimes called as the unity element. So rings with unity are often studied in ring theory. So those special rings which also have this special property that R minus 0, the forget the 0 element, the rest all of the elements form a multiplicative group, commutative multiplicative group. Such special rings are called fields. So fields are also important in algebraic geometry. That's why and another concept in rings is the ideals. Ideals are special subrings in the sense that you take did I write it in my slides? Let me try writing that. So I think I'm not sharing. 1 second. So now I'm sharing. So sorry, I'm not able to get the pen. 1 second. Yeah. So what I said till now is you could take k x1 x2 blah 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 xn. This is the polynomial ring, and I just said that k could be c, and you could just say x1 x2 c x1 x2. I also gave an example in r x1 x2. So these are the polynomial rings I'm talking about. But yeah, what I was just now talking about is that I was talking about the ideals in such rings. These are all polynomial rings. So, for example, if you look at the set of even integers, this is a subring, a very special subring of Z, in the sense that you take any A belongs to Z and R belongs to Z, then R times A belongs to Z again. So, so in general, let's say I in a ring R is called an ideal if uh, for all A belongs to I, R belongs to R times A belongs to I again. Okay, this is called as the left ideal. Similarly, A times R also belongs to R. This property is true. It's called as a right ideal. First of all, I is a subring, and then this property holds. So, in general, if you don't specify anything, I is a two-sided ideal. Now, ideals are very important for uh, algebraic geometry. That's why I I was I was indicating this. Second. So here is the slide. So so these ideals, right? In general, PZ is always a subgroup of Z, and so it's a subring of Z. You can check that, and then this subring has the ideal property also. Now, geometry is intricately connected to this algebra and number theory. So, as I said, just let S be a collection of k polynomials from such rings, whatever I discussed here. What is the ring I discussed? This kind of a ring. So, let's fix in general the polynomial ring k x1 x2 dot dot xn. These xi's are indeterminates, and in this let's pick f1 f2 up to fk. Now if I look at the zero set of s, by zero set of s what I mean is this: zero set of s is set of all x1 to xn such that fi of x1 to xn is equal to 0 for all fi belongs to the ring k x1 to xn. Sorry, for all fi belongs to s. Okay, so if you pick all those tuples which satisfy these equations simultaneously, so that thing is called as a zero set. So given as a bunch of polynomials, we find these zero sets, and these are called algebraic sets, what I mentioned in the first part. So if these algebraic sets are coming from an affine space, like these are all obviously these are coming from Kn, therefore this is called as an affine algebraic set, right? So I have to give examples. I already gave if K is R, and if you consider R x1 x2, then these loci, for example, just fix S to be simply x1 square plus x2 square minus 1. If this is the function, then what are all the tuples which I mean pairs which satisfy x1 square plus x2 square is equal to 1, or x1 square plus x2 square minus 1 equal to 0. So the 0 set is simply the unit circle, right? So unit circle is an affine algebraic set. Similarly, your most of your conic, all your conic sections, the ellipse, etc., are algebraic sets. So similarly, I said we have projective algebraic sets, and irreducible algebraic sets are algebraic varieties. So that's the gentle introduction to what we study in algebraic geometry. The objects are algebraic varieties. They are varieties. These are varieties because they are irreducible. You can't express the circle as union of two. As I said in the beginning, you can't express it as x1 union x2, where each xi is an algebraic set. You can't express that. Therefore, they are irreducible. And irreducible algebraic sets are called algebraic varieties. So that's the gentle introduction, and yeah, I think Chidanand's question was about the topology of algebraic varieties, and that we will carry it forward to the next lecture. Thank you. Bye.